Let's start. So today's topic is angular blah 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 rigid body. So angular velocity of a rigid body, angular momentum of a rigid body, rate of change of angular momentum of a rigid body, and how to use all of these things. And if I can think of it, I'll save 5 minutes at the end for questions, random questions about the prelim. So you can spend the lecture thinking of short answer questions about the prelim. So what is angular velocity of a rigid object? And in all cases here, we're going to be limiting ourselves to 2D. The 3D case is much more confusing and difficult, and we're not going to cover it at all in this course. So working in 2D, we have this key facts. And the key facts are these two things. All pairs of points on a rigid object go in circles around each other. That's the first key point. And the second is the rate of change of angle of any orientation line on object is same as for all others. And this gives us this concept of omega. So let me try to show you with pictures what I mean here. Is if I have some object here, and it's translating and rotating. So this is any old thing. It's an eraser. And it's an eraser that we're going to catch at any instant in time that we like as it's moving around, or my mouse looking at the side, or a book, or anything we like, or a car. Whatever it is, we're going to catch it at some instant in time, which doesn't mean we're going to freeze it. It means we're going to be looking at its motion at that instant in time. And at that instant, if we pick 2 points here, A and a point B, and we look at the motion of B relative to A, we get the following thing. Motion of B relative to A is here is A, and no matter how A is moving around, B is going in circles around it. On the other hand, if we pick some other point here, C and D, and we look at instead the motion of C relative to D, we'll have D fixed here, and we'll have C going in circles around it. So all that can happen is if you focus on any one point on an object and look what another point can do, all it can do is go in circles. So if I take this book and I mark a point here and I mark a point here, call this A, call this B, as this book goes around in crazy ways, if you focus your eye on A, so we're only going to look at the motion of B relative to A, all you see is this. So the motion of any point relative to any other point is it just goes in circles around it. What are you hearing? Bang, 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 crash, crash. Okay, that's one thing. The other thing is if we draw lines connecting these points, we can draw any lines we want connecting these points. For each line, we can look at a theta. Here's a theta 1. Here's a theta 2. Here's a theta 3. So any line segment we draw, we discover or notice that theta 1 dot is theta 2 dot is theta 3 dot. You can try to prove this, but it's not really worth proving. It's pretty obvious that if you rotate one line, they all rotate the same amount. So the rate of change of all of them is the same. And so we call that rate of change omega. And this is the angular velocity of the object. And you can write it as a scalar like that, or we can write like this and call this the angular velocity vector. And the reason we might want to think of it as a vector is, one, is someday we might take a three-dimensional course, and in the three-dimensional course we have to think of angular velocity as a vector. And two is, as a vector we can use formulas that have cross products in them that give us reasonable answers. Just like in a planar motion we have I, j, and k sticking out, sometimes it's useful to think, for example, that E theta is k cross ER. So it's useful to use that cross product with k even in a two-dimensional problem. Okay, so this is this concept of angular velocity of an object. And it's a slightly different concept than what we've used angular velocity for in the past. And the slightly different concept is that it's not the rate of change of a particular angle, it's the rate of change of all lines, the angles of all lines on the object. So if all we have is one dot and we're looking at this motion relative to the origin, in polar coordinates we keep track of it with theta. We say the rate of change of theta is omega. That's really a sloppy use of the symbol omega, which we'd mostly like to reserve for this meaning, which is the angular velocity of a rigid object. Okay, so from this follows the most important formula in rigid body dynamics, which is the following. Let me just write the formula down, and then I'll draw pictures to justify it. It's that the velocity of B relative to A, by which we mean the velocity of B minus the velocity of A, or we mean by it d by dt of the position of B relative respect to A. This is a thing we're interested in. This thing is equal to omega cross the position of B with respect to A. So this is the most key kinematic formula for rigid body mechanics. And let me show you a picture that shows you how it goes. Here we have our object here, and this object has an angular velocity omega, and we've got some point here A, and we've got some point here B. And if we want to look at the velocity of B with respect to A, well, all B can do with respect to A is go in circles. So it's in the process of going in circles with respect to A, no matter how this whole object is moving. It's moving around in crazy ways, but when we look at B with respect to A, it just goes in circles. And so the velocity of B with respect to A is in this direction. And how big is that velocity? Well, it's how fast this is going in circles, theta dot times r. So certainly the magnitude of the velocity of B with respect to A is equal to theta dot times this distance here, which is the magnitude of B with respect to A. But the direction of velocity of B with respect to A is perpendicular to r B with respect to A. So we know the magnitude and the direction, and we say let's look at this vector and just look at the answer and make sure it does the right thing. Omega cross r B with respect to A. This thing, omega, is theta dot k. When we take this cross product, is k crossed with r B with respect to A, which is in the right direction. And then if we look at the magnitude of the vector, well, k is perpendicular to r B with respect to A. So the magnitude is the product of the magnitudes times sine of theta, which is 1. And so the magnitude is just the magnitude of this vector times the magnitude of this vector, which is theta dot. So this is the right answer. So this is in the right direction. Look at the right hand rule. And has the right magnitude. Which was theta dot times r b with respect to a. Okay, so this gives us the right answer. Now we know the motion of one point on a rigid body relative to another. From that, we can figure out the velocity of any point on a rigid body. So let's look at that. Velocity of any point on a rigid body. And if we want to make it maybe a little more entertaining and engaging, let's just, rather than present it as something boring to memorize, let's present it as a question. If somebody tells you how fast an object is moving and how fast it's rotating, can you figure out the velocity of point B on the object? So what we want is, given, say, the velocity of point A on an object, and given omega, and given the location of one point on the object, and given the location of the other point on the object, can we find the velocity of point B? So you can think of that as a homework problem, a test problem, quiz problem, whatever. In fact, let's make it a quiz problem. So, is there enough information? And A and B are on the object. Okay, so work in pairs on this. And while you're working in pairs, I'll think of candidate answers to put on the blackboard. So talk about this. The question is, if you're given these things, can you find this thing? The blackboard, and you have 5 seconds to select an answer. Ready? Five, 4, 3, 2, 1. Oh, what'd I do? Okay. So this one, A, is correct, but it's not in terms of the things that are given. It's the answer in terms of the answer. So it's true that VA plus VB minus VA is VB, and it's just mathematically true. You just cancel these two terms. But it's also meaningfully true, and it's how you get to this answer, which is that VB is VA plus the relative velocity, but the relative velocity is omega cross the relative position, so C is the right answer. Any questions about that? Okay, now let's try a different question. Given the velocity of B, which is some point on the object, and omega, find a point on the object, and we'll call this point A, with the velocity of A equal to 0. So we're given some object is moving around in some crazy way. We're given that this point has some velocity, v. That's the velocity of b. We're given that this thing is rotating at some rate omega. Is there some point on this object that has 0 velocity? So let's make this a quiz again. And we'll go like this. And answer E is cannot be determined. So the question is, can you find such a point? And let's make this a quiz question again and go to it. What is it the velocity of A with respect to? So in this class, we've made a notational decision that if we write something like this, RA, what we mean by that is the position of A with respect to O. So if something doesn't have a fancy subscript, it always means with respect to some universally accepted reference point. So for example, if you write the velocity of A, it always means the velocity of A with respect to some point. And not just any old point, some point which is fixed in a fixed reference frame. So we always have in the background, for any problem like this, is assume that there's a fixed reference frame, and in that fixed reference frame, there's some point O, which we're using to keep track of things. And we're using those coordinate system to keep track of rotation. Does that address your question? That's always implicit. Okay. Does anybody have an answer? Raise your hand. 1 or 2 people. Okay, so we're going to use an honor system here. We're just going to work out the answer, and then we'll write it up here, and you guys will check off whether you had the right answer or did not have the right answer. Okay. And if more than 4 or 5 of you vote right answer, then we have an honesty problem in the classroom. Okay. So what do we know is we know that the velocity b is given to be this thing. And we know that all the points here are going in circles around b. So what we know that we're trying to find the velocity of a, which is equal to the velocity of b plus this velocity of b of a with respect to b. I've done it backwards here. And the velocity of a with respect to b for any candidate points here is tangent to a circle. And we want to add that to this and get 0. So it has to be that the tangent to the circle is anti-parallel or parallel to this line. And what points have velocity relative to b, which are parallel to this line, is the ones that are on the perpendicular line. So this point A, if it's going to be somewhere, has to be on this line. So points over here on this line have velocity that are in this direction with our assumed sign convention that omega is positive counterclockwise, which is the assumed sign convention. Points over here have a velocity in this direction. And we need this to cancel this. So it must be that our velocity of of A with respect to B has to equal minus the velocity of B. Now I carefully erased that board because I was thinking ahead, but I was thinking, oh yeah, I have this board to work with. So what we have is that 0 is equal to the velocity of b plus the velocity of a with respect to b. Why is that 0? Because we're trying to find a point where the velocity of a is equal to 0. Is that clear? But the velocity of a with respect to b, so we have vb is equal to minus the velocity of A with respect to B. But that's equal to minus omega cross the position of A with respect to B. So you can't argue with that, right? Because this is our formula for relative velocity. The problem is we need to try to find this thing, and it's buried inside this equation. So now we have this geometry vector problem of solving this equation for this quantity. We can try to do it by drawing pictures, or we can do a little trick here, which is we can take this equation and take the cross product of both sides with omega, and then this tells us that omega cross the velocity of B is equal to minus omega cross the position of A with respect to B, which looks like a horrible mess because cross products are already a mess, and now we've got a cross product of a cross product, and that's even more of a mess, but that's life. Fortunately, all the vectors here are perpendicular to each other. Omega cross RA with respect to B is tangent to the circle that's at the tip of B. Omega cross that is pointed in the minus RA with respect to B direction. And then we get a vector which is in the minus direction of RA with respect to B multiplied by omega squared. So this turns into minus omega squared R of A with respect to B, which is omega squared R of A with respect to B. Therefore, R of A with respect to B is equal to omega cross velocity of B divided by omega squared. Therefore, I can just write it in here, the position of A is equal to the position of B plus this thing, omega cross VB divided by omega squared. And we have all the other wrong answers. Okay, any questions about that? If we want to check it, it says the position of A is in this point plus a vector which is omega cross VB. Omega cross VB is that way. So it's this vector plus something in that vector, in that direction. So this is the position of A with respect to B. And how far do we go in that direction? Well, we go in that direction a distance of 1 over omega. This gives us the right direction. We could think of this as a unit vector, and then we have down here just 1 over omega. We go 1 over omega out this way. Why is it 1 over omega? The faster this thing is spinning, the less far out we have to go here to cancel the velocity. Okay, so you can vote E, A, B, C, or D. Now, if a lot of you vote A, remember, we know your names. So in principle, I could ask you, is that really what you wrote on your paper? You only get credit for A if you wrote it on your paper. Yeah, I guess I have to accept this, but how come when I said how many people got this answer, only 4 people raised their hands? Can I see some people raising their hands who did not raise their hands when I said, did you get the right answer? Now, come on, you can't all be this dishonest. Are you just sneering at me and going, well, one of you who, okay, if you just voted A, raise your hands. Raise your hands high if you voted A. Raise your hands high if you vote A. God, you guys are just smirkers. I'm gonna get names and find out who you are. Okay. Okay, now we want to do mechanics of a rigid object. And towards the end of doing mechanics, we need to use angular momentum balance. So how do we use angular momentum balance? Is our key result is that when we have some object here and we keep track of some point which we call the center of mass, and this thing is rotating around this way and that, and it's moving this way and that, and it's got some velocity, some acceleration, some angular acceleration. We've got some point here, C. It can be wherever we want. We've got some origin here. The key quantity that we're interested in is the angular momentum with respect to C, which is the position of the center of mass relative to C, crossed with the mass times the velocity of the center of mass, plus omega, plus this quantity which we call omega k, and we multiply this by the moment of inertia in the I, moment of inertia I about the center of mass. Now this thing is a shorthand for, say, the summation of the position of all the particles relative to C crossed with the masses of all the particles times the velocities of all the particles. And why these two things are equivalent is a little bit of algebra which is in the text. So once you've done that algebra, we can also get that the time derivative of this quantity, which is the thing we need for mechanics, is equal to the position of G with respect to C crossed with the mass times the acceleration of G plus Ig alpha k. And this thing alpha will define to be omega dot. And from this we can do mechanics problems. So the most famous of these mechanics problems is the pendulum. So let's work out the pendulum. And just like you had to learn the point pendulum inside out and backwards, you have to learn this so-called physical pendulum or rigid object pendulum, not point mass pendulum. You have to learn this one inside and out sideways also. What we're imagining is we take some rigid object and we hinge it about some point here, and we'll call this hinge point O, and the center of mass of this object is, say, here. Let's call this G, and we'll keep track of where this object is by paying attention to the angle of G relative to vertically down, and we will pick a coordinate system that looks like this, that has I down and J to the right. And the reason we pick that coordinate system is so that if we want to use simple polar coordinate formulas, we don't have to derive them all again. We can use things like x equals r cosine theta and so on. And we have here a G going down, and we would like to know how fast this thing swings back and forth. Okay, so this was actually a problem from freshman physics, but we're going to do it a little differently than freshman physics. So here's the example. We want to figure out how fast this swings back and forth, or we want to figure out the reaction forces on the hinge. What is our main governing equation? And that's going to be true for the rest of the course, and I've said this before, is that the sum of the moments relative to some point C is equal to h dot relative to some point C, and that's equal to this quantity here, which we now understand because we know what angular velocity is. Okay, so how do we work this out? Is we draw a free body diagram of the system. So to draw a free body diagram of the system, I don't need to make it so complicated looking. I need enough geometry I asked them to go out there and beep persistently when I got to the important part. That's like a little dotted underline that's supposed to go into the lecture. Okay, so we have acting on this thing gravity force. And if we can put mgi here, or give it mg and have it implicit that it's times a unit vector in that direction, for a rigid object, gravity forces are statically equivalent to, dynamically equivalent to, equipolant to, the same as, for all dynamics purposes, a single force at the center of mass. So for a given free body diagram in a constant gravitational field, you can replace the gravity forces with a single force at the center of mass. And then we have reaction forces here. And just to be consistent with the coordinate system, I'll call this just R, Y, and R, X. And I'll spell X correctly with the lines that cross each other instead of half cross each other. Okay, any questions about this? Okay, given this free body diagram, we want to figure out, say, the motion, or we might want to figure out the reaction forces. We have a bunch of equations we could use. Only 3 of them are independent. Often in dynamics, you're interested in how things move and not necessarily the reaction forces. So it's nice to find equations that tell you about the motion without the reaction forces. So you want to finesse finding the reaction forces. So you want to find an equation that doesn't include the things that you don't know, which I call solving the problem the American way. You kill the things that you don't know and don't care about. There's these reaction forces, which are in the sideways and up and down direction at point O. We want to kill those because we don't know them or we don't care about them. So if we take sum of moments about O and set that equal to h dot with respect to O, that's a good equation. So this is angular momentum balance A, M, B with respect to O. What are the sum of moments with respect to O? It's the position of G with respect to O crossed with M, G, I. And then on the right-hand side, what do we get? Is we get the position of G with respect to O crossed with the mass times the acceleration of G plus I, G, alpha, K. Yes?
Is the positive x directly downward?
That is correct. That's right here. This gets erased. Now, in that little bit of theory is a fact, which if I wanted this lecture to be complete, even skipping the theory, I have to tell you what this IG is. IG means the integral, or the sum, of the positions of all of the points. And you take the magnitude of the positions, squared it, added up dm. So this is called the polar moment of inertia. And you can calculate the polar moment of inertia of an object relative to any point. You can calculate the polar moment of inertia relative to the point O. For this pendulum problem, it's actually a little bit shorter to use the moment of inertia about point O, but I'm not using that method because it doesn't work for more complicated problems. It only works for the pendulum problem. So I could replace this equation with a single equation that looks like this, that has an O up here, but I don't like that equation because it's not general. Okay, so now to make use of this thing, I've got to evaluate all the stuff here in terms of useful variables like theta, omega, alpha, because that's what I need to get a differential equation. So I assume that I know the mass, I know this distance here, let's call that distance d, and I know the position, I know the angular velocity, and I'm really trying to find this thing because I would like differential equations that I can solve and put into my midpoint method or Euler method or RK45 method. How do I do that? Well, I can invent a direction here I'll call ER, and therefore this thing is D times ER. This thing is d times ER. This thing is just a point going in circles. So what's the acceleration of a point going in circles? It's a minus omega squared, the position of g with respect to O, plus an omega dot times k cross the position of g with respect to O. That's the theta double dot term in the formula for polar coordinates for acceleration. Now if I put these things together and then do these cross products, I have an ER crossed I. So I have an ER crossed I. That's in the minus k direction. So that gives a minus d sine theta. So that's a minus d mg sine theta k. That's what I get on the left-hand side. And on the right-hand side, I have this DER crossed with all this stuff over here. So I have to work out all of these cross products. So I have a D that's common to all these cross products. I have an M, which is common to all these cross products. In the end, all the cross products are going to be in the k direction. I'm going to add to that my I, G, alpha, k. And now I have to work out what's the cross product of ER with this thing and what's the cross product of ER with this thing. Okay, what is the cross product of ER with this first term? Okay, use the rule that I'm sleeping in lecture. The professor all of a sudden asks me a question and goes, and what do you say? 0? Exactly. Good guess. Okay, so ER is parallel to this position. That's the way it was defined in the picture. And the cross product of two parallel vectors is 0. So we get 0 for that first term. And then the second term has an R crossed with k crossed R. K crossed R was in that direction. R cross k crossed R is sticking black out of the blackboard. All of these vectors were perpendicular to each other, so all we're pulling out of this is the magnitude. We already got the d part. We get an omega dot, and then we get the magnitude of this vector. So this turns into an omega dot d, and the k I've already factored out here. So then this whole thing turns into a d squared m plus I g, all multiplied by alpha k. Now if I take this expression and take the dot product of both sides with k, then I can get that alpha, which is omega dot, is equal to a minus d mg sine theta divided by ig plus md squared. So I get this differential equation. Okay, any questions about this? Anybody want me to talk through any part of it again? Yes? Where I got which term? Middle board. What term do you want? This collection of terms here? Is that what you're looking at? Okay, this is just polar coordinate formula for acceleration that you've used all along. Polar coordinate for acceleration says we have a minus theta dot squared r. That's a radial acceleration, and a tangential acceleration, which was in the e theta direction, which was theta double dot times the radius in the e theta direction. So this whole thing here, if we like, is theta double dot d e theta. Okay, any other questions? Yeah?
In the second line on the third board, where is omega dot?
Where is omega dot? Omega dot is here. Alpha equals omega dot, and omega dot is here. So that's alpha, which is the same as omega dot.
Okay.
By definition. We have alpha means angular acceleration means omega dot. Okay, other questions? Now, let's say we wanted to know what the reaction forces are here. We could use angular momentum balance about a different point to figure out something about the reaction forces, or we could just use linear momentum balance for the system, which would give us two equations for these two reaction forces. In linear momentum balance for the system, we would find the acceleration of the center of mass as part of what we need to know to find these forces. But by finding this omega dot, we have implicitly found the acceleration of the center of mass, so we could calculate the reaction forces. Could, should. It's definitely a skill you want to have within the next week or two. Okay, any questions about the prelim tonight? Yes. When do you use moments about a line instead of moments about a point? When you take moments about a point, the meaning of that is moment about a line in the k direction. So the moment about a point actually isn't a concept that we've used. We're always using moment about a line. In 3 dimensions, moment about a point is a vector quantity. And each component of that vector is moment about the line, x-axis through that point, y-axis through that point, z-axis through that point. So probably the answer to your question in terms of practical usage is in 2D problems, you think of it as moment about a point because you're not always drawing the line out of the page. In 3D problems, you're always using moment about lines. If you care about moment about 3 lines through a point, you call that moment about a point because the 3 components of that vector are moments about a point. Does that address your question? The fundamental concept is moment about a line, and if you go back to chapter 2, the cross product section, the whole cross product section is motivated by the concept of moment about a line. Okay, other questions? No other questions. Okay. Yeah. Oh.
We have 3 hours for this test.
It is a 1.5 hour test. You're supposed to be able to get it done in 1.5 hours. I'm designing it for that. If you want to stay late, I give you extra time up to 1.5 hours.